Hello and welcome to another video on basic fiber optics. Today we're going to discuss power limits to data rates in optical fibers. So if you look at a typical undersea fiber optic cable, you'll notice that it consists of a very long fiber span, typically around 100 kilometers, followed by an amplifier, followed by another span, followed by another amplifier, followed by another span until you reach the other continent you're trying to communicate with. But a really good question is, why do we bother to put amplifiers in the middle of the ocean like this? Why couldn't we, for example, just put all of the amplifiers in the very beginning of the span and generate a very high power signal that then propagates all the way to the other end without needing to bother with putting amplifiers inside of the water? We could just have all of this on dry land and still get the same performance. But since we don't do this, there must be some good reason. To understand this, let's consider a basic fiber optic telecommunication setup here. Over here on the left side, we have a string of bits that we'd like to send to the other side here. So one way we could do that is to use this bit stream in order to pulse a laser. For example, if we want to send a 1 down the fiber, we'll turn the laser on. But if we don't want to send a 1 but send a 0, we just turn the laser off. Then this light, or maybe even the lack of light, propagates down the fiber to the other end, where an analog to digital converter is configured so that reading a high optical power will interpret the signal as a 1, and reading low power will interpret as a 0. So this type of basic modulation scheme is called on-off keying, and it's probably the most simple one you can imagine. But we can actually do a little bit better than this and send more data per pulse down the fiber. One way of doing this is to conduct what's called amplitude modulation. The idea is that instead of sending only a single 0 or a single 1 at a time, we divide the bit string up into segments. So first we have a segment called 1, 0, and then we use that to set the laser power to a specific value. For example, let's say this is 75% power. Then we can set the a 1, 1 to be equal to 100% power, and so on and so forth. So that way, if the ADC over here records a very low power, it'll know that we meant to send a 0, 0. If it records, let's say, 25% power or whatever, then it'll be a 0, 1, and so on and so forth. So in this sense, we're actually sending 2 bits of information per pulse down the fiber. Now the question arises, why don't we simply subdivide these levels indefinitely? We don't need to stop at 4, we could do 8, 16, and so on. But there's the reason why we can't do that for realistic case, which is attenuation. So even if the levels are really clearly well separated up here in terms of power, then because of loss inside of the fiber, which typically causes the power to decay exponentially, we can have a situation where these well-distinguished levels over here will actually end up at the 0, 0 down here because the signal gets so weak, and of course then we can't send any data. So a lot of fiber optic engineering is actually about trying to mitigate this kind of loss in order to ensure that we have clearly distinguished levels over here at the other end. One way we can mitigate this is by using an EDFA, or erbium-doped fiber amplifier. The idea is that we can send a signal down the fiber, and even though it decays, then when it reaches an EDFA, we simply boost the power back up to a substantially higher level, and one that's clearly separated into the appropriate power levels over here, so we can once again detect the signal. So if the EDFA can just do this for us, then I guess we're all completely safe and there's going to be no problem with the signal. Well, not quite, because every amplifier that we put in adds a little bit of noise on top of the signal. So instead of a nice, clean, sort of smooth power here, we get a bit of sort of fuzziness in the amplitude fluctuations on top. Which, of course, if we have many amplifiers, many spans in a row, then we're going to get so much noise that, let's say, this level here can start to overlap with this one, and we measure the wrong data that we intended to send. So one way you can think about it is that an EDFA can increase the power of the signal, but it'll always decrease the signal-to-noise ratio, because even though it scales up the power of the signal coming in, it also adds a bit of noise signal on top of it. So this essentially explains why we can't just put a bunch of amplifiers at the end of the fiber span like this. So if we send a normal signal into the fiber at this end and propagate it through all the whole distance and put a bunch of amplifiers, well, at this point, the incoming signal is going to be so weak that the added noise from the amplifiers will simply overpower it, which means we get a low signal-to-noise ratio, which means we can't distinguish the levels, which means that we get just junk data coming through. So that's why this configuration doesn't work. But the one I showed you in the beginning is actually where all the amplifiers are in the very start of the fiber span. So why can't we do that? Why can't we have a setup like this where we just boost up the power to a very high level, send it down the fiber, and then detect it on the other end? So essentially that would look a little bit like this, like we just have very high power here at the launch end, so high that I can't even put it on the screen here. And then we have some attenuation, of course, but if the attenuation is still fairly large, well, if you have large power, it doesn't matter, because it's just going to end up down here at the correct level. So why can't we just get away with doing this? Well, the reason is something called nonlinear effects in optical fibers. Essentially, if you have an extremely high power pulse, then the very strong electric field that the pulse has, it's going to change the refractive index of the fiber. So when the refractive index changes, you also change the phase of the light, which can distort the pulse in all kinds of strange ways. I'm not going to go into the exact details here, but just rest assured that if you have a very high power pulse, then this nonlinear effect caused by the high intensity of the pulse will actually disturb the shape of the most intense pulse. And you can see that kind of scrambles some of them. It can even mess up the way that we detect it on the other end here. So there's a hard limit to how much power we can send down before these effects start to kick in and therefore scramble our signal. And again, what I'm showing here is simply a potential effect that you could have if you have just a single wavelength being sent down. But this gets even more tricky if you're sending multiple wavelengths at the same time, because then some of these nonlinear effects can actually transfer power between different colors and that can really mess up the whole system. So this is really quite an annoying thing to have to deal with. So in summary, we have some kind of trade-off between the launch power that we're sending into the fiber and the data rate, which is related to the signal-to-noise ratio. In this limit right here, where we have low launch powers, then we can have very many sort of amplitude modulation levels, and also our signal is very susceptible to amplifier noise. In the other regime here, if we have very high power, then we have too many nonlinear distortions to send a reliable signal down the fiber. But somewhere in between, there's some kind of sweet spot, where on one hand, the power is so high that we can have a lot of different levels that can be reliably detected by the analog to digital converter, but we don't have so much power that nonlinear effects start to kick in and disturb the signal. And if you want to work in like fiber optic network modeling, this kind of curve here is something you'll definitely see sooner or later, and try and figure out, well, for this fiber span, like how much launch power should we send in order to maximize the data rate. Some perspective to think about is that in this presentation I only discussed amplitude modulation, but in reality we don't just modulate the amplitude in order to send data, we also modulate the phase of the light. So for example, as shown in this diagram over here, this point right here in the constellation diagram has a certain amount of power, which is given by the distance from the origin here, and it's the same amount of power as this point up here, but because they have different phases, then you can also use that to encode different strings of data. And of course, if you consider that amplifier noise doesn't just affect the amplitude, but also the phase, and also consider that nonlinear distortions typically affect the phase quite a lot, this is something else you'll have to keep in mind. Another effect that is important to consider is dispersion, which essentially refers to the temporal broadening of very short pulses inside of a fiber, which occurs because a short pulse like this consists of many different frequency components, and if the refractive index is a little bit different for different colors, then some frequency components will propagate slightly faster than some other ones, and then that'll cause the pulse to spread out over time. Now, this is a limitation in of itself, but the amount of dispersion also affects the magnitude of the nonlinear distortion. That's another factor to keep in mind if you want to do this kind of modeling. Finally, something to maybe keep an eye out in the future is experimental low-loss hollow core fibers. Essentially, in a conventional optical fiber, we have a glass core with a slightly higher refractive index than the surrounding cladding. And in that case, it's total internal reflection that guides the light all the way down the fiber. And the nonlinear effects take place in the inside of the core because the glass gets affected by the strong electric field. But in a hollow core fiber, light isn't guided by total internal reflection, but rather by Bragg reflection over these interesting glass structures right here inside of the fiber, which means that we can have a perfect vacuum inside of the fiber and still send light down the middle of it. And if we have a perfect vacuum, there's nothing for the high intensity field here to even modulate. So there's not going to be any nonlinear effects. We can actually, hopefully, reduce the need for sort of amplifiers in the middle of a long fiber span. Work is still being done in order to make these kind of fibers sort of both give them low enough loss and also make them cheap enough for this to be viable, but it's definitely something to keep an eye on in the future. Thank you for your attention.